In this video, we will learn about the consistency and some other stuff for the numerical method. This is very important lecture in my point of view on numerical method. The reason is without this criteria, we cannot say that a numerical method is acceptable or not. So for numerical method, we have three conditions to fulfill. The first one is consistency. And the second one is stability. And third one is convergence. Although I already defined these quantities or these terms in some other of my lectures on numerical method, but I will just review it over here. So numerical method must fulfill all these conditions. In the history, there are numerical methods which are developed by some scientists, but at the end, they were useless since they could not satisfy these three conditions. So what are these conditions? The first one is consistency. Consistency means that if we have a function, for example, if our flux is fq is equal to constant, so it means that the numerical method must follow that the old value and the new value and the constant value must be equal, and our flux will be q bar that will be equal to f of q bar. So this is our observation that the numerical method must follow this method. What is the actual definition? The actual definition is the truncation error of a numerical method must approach to zero as you refine the grid delta x and delta t approaches to zero. Before moving further, I just want to make a comment over here. The numerical method that we study in this lecture series is finite volume method for PDEs. Since finite volume method and finite difference method are same for second order method, second order method. So the consistency, stability, and convergence is actually derived for finite difference method. The formula for these two methods is same as I already mentioned to you. So we don't have a new criteria like consistency, stability, and convergence for finite volume method. So what we do, we have finite difference method, these criteria available to us. When we apply that to finite difference method, it automatically is applicable to finite volume method as well. Okay, we saw that maybe I write again, the numerical method for finite volume method was qn plus 1i qni minus delta t by delta x. And when we have, for example, q n I plus 1 minus 2q n I plus q n I minus 1 divided by, it should be delta x square. I don't divide anything over here. So this formula is the same as for finite volume method and finite difference method. The only difference is in finite volume method, we construct a formula by taking an average qn 1 over delta x and xi minus 1 half to xi plus 1 half. Then we integrate that function Tn dx, then we get the average over here, Qni. That's how we constructed finite volume method. But for finite difference method, such construction does not exist. We actually make a Taylor's, we write a Taylor's function in terms of Taylor series. We apply Taylor series and get the answer, get the numerical method. So these two numerical methods, the end product is same for these two methods. So we apply these three criteria to the finite difference method. Actually, these were developed in 1950s for finite difference method. And when we saw that there is a formula is same, so why don't we use that for finite volume method as well? So this is the idea that you must remember. Okay, so what we have for consistency, we have truncation error approaches to zero as delta x and delta t approaches to zero. Then at the end, the second one is the stability. Stability says that, for example, if we have a solution, for example, if we have an exact solution like this, and your numerical solution behaves like that, then it means that there are oscillations and the method is unstable. This is the numerical method which is unstable. The unstable method, we don't want unstable method. So stability is also very important. It can happen that if sometime the numerical method follows consistency, but it is not stable. Okay. And also, for example, if we have a exact solution and then we have a numerical solution like this, although it is converging towards the this curve, but still you can see that there is oscillations. The oscillations are not desirable in this scheme, in this numerical method. So we need to find out a way whether the numerical method gives you oscillations or it is a stable method. Okay. So this was the second criteria for numerical method to hold. And the third one is the convergence. Convergence is the same thing that we say that the numerical method must approach to the exact solution. That's how we call it convergence. But it is, in theory, it is very difficult to prove the convergence. How you can say that the numerical method approaches to the exact solution? The idea is visually it is like this. For example, we have numerical method. As we increase delta x and delta t, then in fact we decrease that value, so the numerical solution approaches to exact solution. Okay, this is called convergence, but we need a mathematics for that. But fortunately we have a one theorem which is Lax equivalence theorem. Lax equivalence theorem, which says that if you check consistency, which is easy to check, we will talk about that in the next videos. You find out the truncation error and make it approach to zero, while delta x delta t approaches to zero, then it is consistent problem. Then stability, how you check stability? You check stability by Fourier analysis, and we will talk about that as well, Fourier analysis. And when we have consistency and stability, then the theorem says that your numerical method is convergent, and it is a blessing for us that we have a numerical method convergent if we just check that these two conditions. This is due to the theorem. So Lax actually introduced this theorem. Okay. So this was all about a very philosophical discussion. Over here, there is no mathematics involved. So we will talk about consistency. I will probably use consistency for some different numerical methods in the next video. So you will become comfortable about consistency. And then the next video, maybe I will talk about the stability, where I apply the Fourier analysis. Von Neumann analysis is, it is also called. I will apply that, and we will have a stability analysis. And convergence is easy due to the theorem. So thank you for watching.